Welcome back. Today we will discuss fluid statics and how the pressure within a fluid changes. We imagine a small surface immersed in a fluid. We have seen in the first lecture that a fluid at rest or in uniform motion cannot apply a shear force on a surface. The only possible force is thus normal to the surface, whatever be the orientation of the surface within the fluid. This force is compressive and depends upon the area of the surface. This force is termed as pressure. The pressure is measured as force per unit area and its units are Newton per meter square. This unit is given the name Pascal and abbreviated as PA. The typical atmospheric pressure on Earth is about 10⁵ Pascal or 100 kilopascal. Let us consider the concept of pressure at a point. Imagine a small triangular element as shown. This is a fluid element. We draw a free body of this element, AOB. On this element, on this vertical surface AO, the pressure forces are acting horizontally all over this area. On the surface OB, the pressure forces are vertical, and on surface AB, they are normal to the surface AB. Let us consider the equilibrium of this element AOB of the fluid. This table lists for the three surfaces the areas delta x, delta y, and delta y by cosine theta for the inclined surface AB. It could also be written as dx, delta x divided by sine theta. If the pressure on the surface AO is Px horizontally and on surface OB is Py vertically, and on surface AB it is Pn normal to the surface, then the x component of forces on the three surfaces are Px delta y 0 and minus Pn delta y divided by cosine theta, which is the total force multiplied by cosine theta, the horizontal component. Similarly, the y component of forces on the three surfaces are 0, Py delta x and minus Pn delta y divided by cosine theta into sine theta as shown. If we write the equilibrium equation for this, sum the x direction forces equated to 0 and sum the y direction forces and equated to 0, we get from the horizontal force balance Px is equal to Pn and vertical force balance Py is equal to Pn. Thus, pressure in the x, the y and the n directions are the same. Since the n direction was taken arbitrarily, the angle theta was not fixed and this works for all angle thetas. We can state that pressure at a point is same in all directions. This is known as Pascal's law. This is a very useful result and we will use throughout this chapter. Again, let us consider a fluid element shown by yellow lines within a fluid. This is the length delta x. On the left end of this, the horizontal force is P times delta A, where delta A is the cross-sectional area of this fluid element. On the right hand side, by Taylor's expansion, the pressure becomes P plus delta P by delta x into delta x, and the total force would be that multiplied delta A. We have shown here only the forces in x direction. Summing these forces and equating them to 0 because the fluid is in equilibrium, we get delta P by delta x is equal to 0. If we did the same thing in the y direction, the direction normal to the screen, we would get delta P by delta y is equal to 0. So there are no variations in pressure in the horizontal direction. Within a fluid, the pressure at 2 points which are on the same horizontal level must be same. Let us see what is the variation in the vertical direction though. Let's consider this element in a stationary fluid in the vertical direction. Let the length of this element be delta Z, and the two pressure forces are shown. On the lower face, it is P delta A upwards, and on the upper face, it is downwards, and we use Taylor's expansion to increase the pressure force. But in the vertical direction, there is one more force on the fluid element, that is the weight of the fluid element itself. And that force is the volume of the fluid element, delta A delta Z, multiplied by rho gives you the mass of the fluid element, and g, this acceleration due to gravity. So that the total force on this fluid element because of weight in the vertical direction is rho g delta Z delta A. If the fluid is stationary, then the vertical force balance gives us delta P by delta Z is equal to minus rho g. That is, the pressure variation in the vertical direction is like minus rho g, where rho is the density of the fluid and g the acceleration due to gravity. Even when the density of the fluid is not constant, the same equation is applicable because we have taken a very small element. So, delta P, del P by del Z would be minus rho g, where rho is the density at the location we are calculating the pressure gradient at. Since P does not vary in the x and y directions, we can write dP by dZ is equal to minus rho g, the only direction in which there is a pressure gradient. Let's now look at the variation of pressure in a fluid such as water, where the density is assumed constant throughout. This is obtained by simply integrating the equation that we obtained in the last slide. Delta P by delta Z is equal to minus rho g, and we integrate this with the condition that P is equal to P naught at Z is equal to 0. The free surface of water, free surface of the liquid. Simple integration gives P is equal to P naught minus rho g Z, where Z is the distance measured from the location where the pressure is P naught in the vertically upward direction. Usually, in the case of liquids, it is convenient to measure the depth not the height from the surface. And the depth from the surface is denoted here as h, and so that we can write P is equal to P naught plus rho g h. For water with free surface exposed to atmosphere, P naught is P atmosphere, which is about 10 raised to the power 5 Pascal, and we plug in the value of rho, which is 10 raised to the power 3 kilogram per meter cube, and of G, then the equation becomes P is equal to P atmosphere plus 9.8 into 10 raised to the power 3 times H in pascals. This is the pressure distribution shown here, which is linear with the depth. This all you must be familiar with from a high school. If we have fluids, a combination of fluids arranged in stratified layers with various density rho 1, rho 2, rho 3 and rho 4, then the plot of pressure variation would be as shown. At the topmost layer, it will start with P atmosphere. Then at the interface with the second layer, a height H1 down, it would become P atmosphere plus rho 1 times G H1. Then we go down further in a layer with the density rho 2 up to depth H2. Then the P2 there would be P1. The pressure at this interface plus rho 2, the density of the second fluid, times G times H2 minus H1, the depth of the second layer. Similarly, the third and the fourth layer. One common expression or one common method of specifying pressures is called the pressure head. We use the term gauge pressure as the pressure above the atmospheric pressure. The name gauge pressure comes from the fact that ordinary pressure gauges measure pressure above the atmosphere. The gauge pressures are usually expressed in terms of how much water column is required to create a given gauge pressure. Consider this bulb containing water, and if the water rises into this tube, a test tube, which is called a piezometer up to this height, then we call that this is the head of pressure within this bulb. The pressure at point A is the same as pressure at this point. Why? Because these are at the same horizontal level. So if we specify head, then we know that the pressure is rho g h. While specifying the pressure as head, we have to specify what fluid. So if the fluid is water, this is h meter of water. That is the head. Let's do an example of conversion of units. What is the head in meters of water for an automobile tire pressure of 30 pounds per square inch? We do the conversion. 30 pound force per square inch is 30 pound force per square inch multiplied by 0.456 kilogram force per pound force, which gives you 13.6 kilogram force per inch square. We want to change kilogram force into Newton, so we multiply this by 9.8 Newton per kilogram force to get 134 Newtons per inch square. And to convert per inch square into per meter square, we multiply this by inch square divided by 0.0254 meter per inch whole square. And if we do this, we get 2.077 into 10 to the power 5 Newton per meter square. And Newton per meter square is termed a Pascal. So this is 2.077 into 10 to the power 5 Pascal, or 207.7 kilopascals, a more often unit of pressure. Now 1 meter head of water is rho of water times G into 1 meter, which gives you 9.8 into 10 to the power 3 pascals. So that 2.077 into 10 to the power 5 Pascal is 21.2 meters of water. So this is the head of water that will create the same pressure as 30 pound per square inch, 21.2 meters. Compare this to atmospheric pressure, which is about 10 meters of water, a little less than 10 meters of water. In fact, about 9.8 meters of water is the atmospheric pressure head. This 21.2 is above the atmospheric pressure. This is the gauge pressure. You must have seen, or you must have heard, that a liquid maintains its level. If I have a U-tube in which I put water, then this arrangement where level in lab 1 is different than lab 2 is not sustainable. How do we show them? We show them using the fact that we have already obtained that the pressure at the horizontal level are same in a liquid. Point 3, the pressure at point 3 is P atmosphere, which is the pressure at 1, plus rho G H1, using the variation in vertical direction, the hydrostatic pressure law, which we derived earlier. So P3 gauge, the pressure above atmosphere, is rho G H1. Pressure at point 4 similarly is rho G H2. But point 3 and point 4 are at the same horizontal level. So pressure 3 must be same as pressure 4. If this is so, then H1 must be equal to H2. That is, the level in the two limbs must be equal for equilibrium. This doesn't work. So this is the correct configuration. It is interesting to construct an alternate proof for the same thing. Suppose a liquid does not maintain its level, and at some location in a liquid at rest, the surface is sloping as shown here. If the surface was sloping, we could construct a small element of the fluid of this triangular shape. This element, a small element, is also at rest. What are the forces acting on this? The forces acting on this are the pressure variations on the vertical face. These are horizontal forces. Forces on the bottom, which are uniform because the bottom is horizontal at the same level. Clearly, this magnitude of force must be the same as this magnitude of force. We have shown forces above the atmosphere, the gauge forces, because we have started with 0 at this. So the upper surface, the sloping surface, is exposed to atmosphere, so pressure is zero everywhere. What are the other forces? Of course, the weight of this triangular fluid element. Now we have got a result. If the configuration of the fluid element was like this, how would the horizontal forces balance? There are only forces in one direction only. So the horizontal forces would always be out of balance if the configuration of the element is anything like this. If the configuration of the element is wedge-shaped. And therefore, the only valid configuration is when the surface of the liquid is horizontal, so that we cannot create a wedge-shaped element. You do know about a barometer, a device to measure the pressure of the atmosphere. A long tube, about a meter long, closed at one end and open at the other, is filled with mercury and is inverted into a cup of mercury. The level of the mercury decreases slightly and then it comes to equilibrium, such that a column of height h is held up into this tube which is closed at the top end. Clearly, this point A, which is the same level as the level of mercury in the open cup, should have the atmospheric pressure. So this point is at atmospheric pressure. So this point here should be at a pressure equal to P atmosphere minus rho g h, where rho is the density of the mercury, g is the acceleration due to gravity, and h is the height of the column of mercury. Now the pressure at this point should be zero because it's vacuum. Actually, it will not be vacuum. It would be the vapor pressure of mercury at the given temperature. But that vapor pressure is quite low. So we can neglect this, and this can be treated as the pressure zero, absolute zero. And therefore, the atmospheric pressure must be equal to rho g h, where rho is the density of the mercury. So if we know the value of h, we can measure the atmospheric pressure. This shows a typical construction of a commercial barometer which are in use in the school laboratories. The lower end of this barometer consists of a cup in which a mercury is filled up. The bottom of this cup is made of a flexible membrane. There is a screw, zero adjusting screw, which we turn to keep the level of mercury in the cup just touching the zeroing peg here. This establishes the zero of the scale, because this tube that goes up there carries a scale with this. The zero of the scale coincides with the tip of this peg. So the length of the column standing above the cup level now, when measured against this provided scale, gives you the height h of the mercury column. The top end carries a vernier, and using the rule of reading verniers, we can read the pressure. In this case, It is this, and this is what is coinciding here. So it is 70.65 centimeters of mercury is the pressure head of atmosphere. 70.6 and then 5, 70.65 centimeters of mercury. You multiply with the density of mercury, which is about 13,600 kilogram per meter cube, and G 9.81, and we can get the pressure. Let us now consider the variation of pressure in atmosphere. You know that as we go up in the atmosphere, the pressure decreases. So how does the pressure change? We use the same equation. dP by dz is equal to minus rho g. But rho is a variable here. The density depends upon the pressure. As the pressure decreases going up, the density too decreases. So we cannot integrate it like we integrated for a liquid when we derived the hydrostatic pressure variation. So here we will have to express the density by using the gas law. The perfect gas law says P is equal to rho RT. So rho is replaced by P divided by RT. And so the equation for the pressure variation becomes dP by P is equal to minus G by RT into dZ. Z is measured upwards. Now this cannot be integrated easily because the temperature itself varies vertically. There are various reasons why the temperature varies, and temperature varies in the atmosphere from day to day, moment to moment, and location to location. But for the purposes of easing the aviation industry, we use the concept of a standard atmosphere. The Organization of International Civil Aviation Agencies have established a standard atmosphere in which the temperature variations is seen to be this. This curve of the temperature variation with the altitude in kilometers is derived from very large number of measurements in the atmosphere, and people from various countries coming together and deciding that this temperature variation best represents the temperature variations in the atmosphere throughout the year and in all locations. It starts with a temperature 288.16 Kelvin at sea level. Then for 11 kilometers, this temperature is decreasing at the rate of 6.5 degrees Celsius per kilometer, or 6.5 into 10 to the minus 6 Kelvin per meter. At 11 kilometers height, the temperature is only 216.66 Kelvin, which is about minus 58 degrees Celsius. This atmosphere up to 11 kilometers is called troposphere. This is the band of atmosphere in which most of the weather activity is confined. Above that, up to a level of 25 kilometers, the temperature remains constant. Then the temperature starts increasing. The layer immediately above the troposphere is called the tropopause. Compare the height 11 kilometers with the height of Mount Everest, which is only about 8 kilometers. So troposphere is present there up to a height of Everest and beyond, and a couple of kilometers beyond that. Most of the flight take place in the troposphere. We can use the equation here to track the variation of temperature with altitude. Using this expression of temperature in the expression of dP by P above, with this temperature we can plug in there and get the pressure variations within the atmosphere. The pressure variations within the atmosphere for the first 11 kilometers is seen like this. About 101 kilopascal at the mean sea level and about 22 kilopascal at the height of 11 kilometers. It decreases by a factor of 5. This variation of pressure with the altitude is used in an instrument called altimeter to measure the altitude of the aircrafts as they fly. This altimeter is nothing but a barometer. It measures the atmospheric pressure. But it is calibrated into altitude in meters or altitude in feet by using the equation that we obtained earlier. The 3 needles will tell you what is the altitude from the given datum. While flying, there are 2 kinds of altitude that we are interested in. One is when we are taking off and coming into land, we want to know how high we are above the airfield, because that is important for safe landing. Suppose your airfield is at 500 meters above mean sea level, and if your altimeter was calibrated only to show the height above the mean sea level, it would read 600 meters when you're only 100 meters above the airfield. This could be quite confusing. So it is always advisable to ask the traffic controller the atmospheric pressure at the airfield. The pilot calls the control tower and says, what is the pressure? And they ask, the word used for this is QFE. QFE are the letters that indicate the altitude above the ground, above the airstrip at which you are going to land. So the pilot asks the air control tower, what is the QFE? And if he gets a reply that it is 29.96, then he sets the reading in this window, the yellow window, 29.96 in inches of mercury. Now, this is an old picture where the pressures are shown in inches of mercury and the altitude in feet. Most altimeter today would show altitude in meters, and this window would show pressures in millimeters of mercury. So by turning a knob, they switch the reading within the window to 29.96, the QFE reported by the tower, and then this would read altitude above the airfield. On the other hand, when you are flying from one city to another over long distances, in the airways in between, we set the window to QNH, which is 29.92 inches of mercury, the pressure at mean sea level or 760 millimeters of mercury. Then your altimeter would be reading pressures, reading altitude above the mean sea level, assuming that the atmosphere is standard. Pressures are used in lot of machineries that we operate, and these machineries are based on the principle of hydraulic force multiplier. Consider two cylinders connected in carrying a fluid. On one cylinder, there is a piston of area A1. In the other one, there is a piston of area A2. If we apply additional force F1 on this piston, this will create an additional force F1 by A1 in the fluid. This additional force would be transmitted everywhere within the fluid. So this same additional pressure F1 over A1 would appear at all points, even at the face of the second piston. And so the force developed in the second piston would be F2 is equal to F1 divided by A1 multiplied by A2. And if A2 is large compared to A1, force F2 would be large. This is the principle of force multiplier, which is used in various devices. Shown here is a fancy pneumatic lift. This lift is nothing but a cylinder within which a capsule carrying the passengers travel. This cylinder is connected to the inlet and outlet port of a air pump, a compressor, would then press the capsule down, and the capsule carrying the passengers would come down. But if we connect the output to the input of the compressor, then it will suck air out from the top and it will decrease the pressure below the atmospheric pressure. The atmospheric pressure is acting below the capsule, and so the pressure difference multiplied by the large area of the capsule results in a large force that carries the capsule up. This picture shows a pressure actuator used in all kinds of hydraulic machinery. What it does is that a fluid at a large pressure is pumped into it, and as it pumps, this acts on this piston, and this piston moves in that direction, applying a force in whatever equipment that we want to apply force at. Example of this is this earth mover. This is a pressure actuator. Applying hydraulic pressures at this end would extend this rod and would make this arm turn in that direction. We can apply very large forces through these actuators. These actuators are also used in controlling the control surfaces of an aircraft. This hydraulic table for lifting loads also uses two actuators in a similar manner. Let's now consider forces and pressure in fluids which are moving as a rigid body. Let's consider a container which is accelerating in the horizontal direction. Consider a horizontal fluid element of cross-sectional area dA. Then the net force on this fluid element in the horizontal direction is P1 dA, where P1 is the pressure on the left face, minus P2 dA, where P2 is the pressure on the right face. And this should be equal to the mass of the fluid element times the acceleration. But the pressure in the fluids depend upon the depth from the free surface. If the fluid is accelerating the horizontal direction, the fluid pressure variation in the vertical direction would not change. So the pressure at this point would be the atmospheric pressure plus rho gh. If the fluid is accelerating, P1 must be greater than P2. So pressure P1 must be greater than P2. So the depth of this phase from the free surface should be more than the depth of this phase from the free surface. This means the free surface cannot be horizontal. The depth have to be different. More above point 1 and less above point 2. Here we have shown this. The depth is h1 above point 1 and h2 above point 2. Clearly, dm, the mass of the fluid element, would be the density rho times dx, the length of the fluid element, times the cross-sectional area dA. Acceleration A, if I plug in this for dm, I get a simplified equation dh by dx is A by g. dh by dx is the slope of this line, is A by g. Acceleration divided by the gravity. Next, we consider a rotating container, a container of a liquid in which is rotating about its axis at an angular speed omega. We see that the free surface of this is curved. If this was a level at rest, then when it is rotating at omega, the curved line becomes the free surface. Again, we consider this small element shown as white at the radius r from the axis. Consider the force balance at the left face of this white element. The pressure is rho gh multiplied by dA. The pressure at the right face is rho g h plus dh by Taylor's expansion multiplied by the area, which is twice by r dz, and this should be equal to mass times the acceleration. And acceleration is the centripetal acceleration r omega square. And so on simplifying this, we get dh is equal to omega square by g r dr. And so by integrating this and using that at r is equal to 0, the depth is h r0, we get this equation for the free surface. This clearly is parabolic. Here I have calculated the free surface for various values omega. The horizontal line is for 0 speed, and as the omega increases, at the center the free surface dips, and near the wall it climbs up.
When only gravity is at play, liquid surfaces in the laboratory are flat and horizontal. However, when we spin this container of water, it rotates as a solid body, and centrifugal acceleration distorts the free surface into a parabolic shape. An accompanying CFD simulation shows colored pressure contours, revealing that the pressure indeed rises linearly downward from any point on the surface, just like the case for a motionless body of water, according to the principle of hydrostatic pressure.